Welcome to chapter 7. So we'll start talking about magnetism. So in this lecture we'll discuss three sections. We'll talk about magnets and magnetic fields. We'll talk about how to get magnetism from electricity, and we'll also talk about the magnetic force. So let's start with magnets and magnetic fields. So after you complete this section, you should be able to predict whether magnets will repel or attract each other. You should also be able to describe the magnetic field around a permanent magnet, and you should also be able to describe the orientation of the Earth's magnetic field. So let's start with magnets. So magnets are materials that contain iron. So these are iron containing substances. So they have two distinct poles. You have a north pole and a south pole. Just like a charge, you have a positive charge and a negative charge. A magnet is a dipole. So a dipole here means that if you split a magnet, if you take a magnet and how many parts you split it into, it always has two poles. For example, let's say if I split it into two parts, so it will again become north south north south. So a magnet cannot have a monopole. So a monopole cannot exist. Just like a charge can have positive or a negative charge, but you cannot have an independent north pole and an independent south pole. Both are interconnected and they will always exist as a dipole. So they always exist as a single structure. So these names originally are derived from the magnetic behavior of the Earth. So like the poles of magnets repel each other. So the like poles, meaning that north and north, south and south, will repel each other. Unlike poles, whereas north and south will attract each other. So just like charges, like charges repel. The same way, like poles of magnets attract, repel, and unlike poles attract each other. So this is a description of a general magnet. So if you see a laboratory magnet, you will generally see the red part. The red part represents that it's the north side, and the silver part represents that it's the southern side. So what is a magnetic domain? So a magnetic domain is a region that is composed of a group of atoms whose magnetic fields generally align in the same direction. We call that a magnetic domain. So there are some materials that possess that magnetic domain. We classify them into permanent magnets. So some materials can be named into permanent magnets. We classify magnetic materials into two types: soft and hard magnetic materials. Soft magnetic materials, for example, like iron, are materials that can be easily magnetized, but they tend to lose their magnetism very easily in a short amount of time. Hard magnetic materials are materials like nickel, which tend to retain their magnetism. So if you take a block of nickel and magnetize the material, that material will retain its magnetic properties for a long time. But iron will lose its magnetic properties very easily in a short amount of time. Now let's talk about the magnetic field. So just like electric field and gravitational field, magnetic field is also a non-contact force, and it's also a field force. So it's also a field force. So a magnetic field here is basically the region where you can feel the presence of the magnet, or you can feel the force applied by the magnet. So we draw magnetic field lines to represent the magnetic field, and to draw magnetic field lines around a magnet, we generally use a magnetic compass. A compass can be used. So when you draw the magnetic field, it looks somewhat like this. So the magnetic field line starts from the north pole and ends at the south pole. This is the idea. This is how the magnetic field of a magnet generally looks like. So the pointing part, notice that north will be attracted towards the south. So this is the south part. This is the south part and the north part. Red is the north part. So the north part will always be away. So that's why the magnetic field line always starts from the north pole and ends at the south pole. So this is how we generally draw the Earth's magnetic field. So Earth's magnetic field is also similar to that of a bar magnet. So here, Earth generally has what we call two types of poles: geographic poles and magnetic poles. Why is it that we have two different poles? Is because of the way Earth rotates. So the axis based on rotation is not the same as the axis of magnetic field. So the axis of rotation, we call it the geographic north pole and the geographic south pole. And Earth actually has a tilt. That tilt is represented by the magnetic field. That magnetic field has a certain angle, so we call there is a certain angle between the magnetic field and the geographic poles. Now, geographically, which is the north pole, we call it the magnetic south pole. Geographic south pole is the magnetic north pole. So this is how we can differentiate between these two. So whatever is it geographically, it's opposite in terms of its magnetic inclination. Now, this magnetic declination is the measure of the difference between the true north and the north indicated by a compass. So this is the magnetic declination or the change in the angle. So the deflection is much less visible at the center of the earth, but it varies very heavily when you go towards the other end, when you go towards the poles. So near the equator, there is the declination is much less evident, but when you go far away from the poles, when you go far towards the poles, you end up getting a lot of change between the magnetic field, the magnetic compass direction and the geographic direction. So this is the Earth's magnetic field. Next, let's discuss section 2. How do you get magnetism from electricity? So after you complete this section, you should be able to describe the magnetic field produced by a current in a straight conductor and in a solenoid. You should also be able to use the right-hand rule to determine the direction of the magnetic field in a current-carrying wire. So let's start with, now let's discuss magnetic field of a current-carrying wire. So a long straight current-carrying wire will have a cylindrical magnetic field. So if you have a wire like this, the magnetic field is cylindrical around the wire. Now, compasses in general can be used to show the direction of the magnetic field that is induced by the wire. So we use the right-hand rule to determine the direction of the magnetic field in a current-carrying wire. So what is the right-hand rule? So the right-hand rule basically, if you take a wire and if you point your thumb in the direction of the current, the way your fingers, the other four fingers wrap around the wire represents the magnetic field. So if you take a wire and if the current is going upwards, the magnetic field is counterclockwise. If you take a wire and if the current is going downward, then the magnetic field is clockwise. So this is how we can determine by using the right hand thumb rule. So this is what it looks like when you have the right hand thumb rule. Now, we talked about the current that is passing when you have a wire and what the direction of the magnetic field is, where the wire is straight. What if the wire is a circle in several loops? So we call those solenoids. Solenoids are the ones that produce really strong magnetic fields by combining several loops. So remember that a straight magnetic field, a straight current produces a circular magnetic field. Now in the same direction here, a circular current produces a straight magnetic field. So here a solenoid basically behaves like a magnet. If the current flows from bottom to the top, the wire starts, so on the left side you have the north pole, on the right side you will have the south pole. So this is what we call as a solenoid. A solenoid is a long helically wound coil of insulated wire. So this is how we can determine the current field. So here it behaves like a magnet where you have a circular magnetic field. Now let's come to the final topic, magnetic force. So let's come to the next section, magnetic force. So after you complete this section, you should be able to give the force on a charge in a magnetic field. You should also be able to determine the strength of the magnetic field. And you should be able to use the second right-hand rule to determine the direction of the force on a charge moving through a magnetic field. And third, you should also be able to determine the magnitude and direction of force on a wire carrying current inside a magnetic field. So let's talk about the charged particles. So what happens when you have a charged particle that moves in a magnetic field? So when a charge moves through a magnetic field and experiences a force, that force is proportional to the charge, the velocity, and the magnetic field. So the magnetic force is proportional to the magnetic field, it's proportional to the velocity, it's also proportional to the charge. So combining all of them, you get Fm equals BQV, and B here can be written as F by QV. So this is the formula for the magnetic field, or F magnetic equals QVB. Now, the direction of the magnetic force on a moving charge will always be perpendicular to both magnetic field and the velocity. So what does that mean? We use an alternative right-hand rule to represent the direction of the magnetic force. So a charge here moves through a magnetic field will always follow, a charge moving through a magnetic field will always follow a circular path. So this we use what we call the right-hand palm rule. So here your palm represents the magnetic field, the thumb represents the velocity, and your other four fingers represent the magnetic field. So the palm represents the magnetic force, your hand represents, your four fingers represent the magnetic field, and the thumb represents the velocity. So you have to place your hand in this direction. Only when you place it in this direction, this is how the directions will work. So these are perpendicular to each other. So let's try a problem and let's see if we can solve this problem. So what is given in the data here? So a proton moving east experiences a force of 8.8 times 10 to the power negative 19 Newton upward due to the Earth's magnetic field. At this location, the magnitude of the field is 5.5 times 10 to the negative 5 Tesla to the north. Find the speed of the particle. So write down everything that is given here. So they have given us the force, which is 8.8 times 10 to the power negative 19 Newton. And you have a proton, so which means Q is 1.6 times 10 to the power negative 19 Coulomb. And magnitude of the magnetic field is B equals 5.5 times 10 to the power negative 5 Tesla. So Tesla is the unit of magnetic field. So remember that. So let's try and solve this problem here. So this is the data that is given here. So we know that the formula for the magnetic field. So the only thing we do not know is velocity. V equals question mark. So magnetic force is equal to BQ times V. So we want to find V. V becomes Fm by BQ. So this is Fm here. So Fm is 8.8 times 10 to the power negative 19 over B is 5.5 times 10 to the power negative 5 times Q here is 1.6 times 10 to the power negative 19. So 10 to the power negative 19, 10 to the power negative 19 gone. So 8.8 by 5.5 times 1.6 into 10 to the power of 5. So let's calculate the value. So 5.5 times 1.6 is 8.8. So you have 8.8 by 8.8. So you get 1 times 10 to the power of 5 meter per second. So this is the velocity of the proton moving in the magnetic field of strength 5.5 into 10 to the power negative 5 Tesla. Notice that all of them are in their SI units. That's why velocity is also in its SI unit, meter per second. So this is how you can use the values and solve the problem. Now we know the velocity, but we want to know the direction as well. So a proton here is moving east and it experiences a magnetic force upward. So let's consider if this is the horizontal ground and this is the proton. Proton is experiencing a magnetic field upward. So this is the magnetic field and it experiences a force B towards east. So which direction is east here? You have east in this direction. So the velocity is in this direction. Then the force is going to be perpendicular to both of them. So which means that it's going to be perpendicular to both of them, which means that it goes forward. So which means that this force here, Fm, is going to go towards the south. V is east and B is upward. Then Fm is going to go towards the south. So this is the direction in which you generally see the magnetic force. So this is how you can calculate the directions. Remember that all of them are perpendicular to each other. So we know that when you draw directions, these are the directions. So this is north, south, north, east, west, and south. And this arrow represents upward, and this arrow represents downward. So all of them are perpendicular to each other. So using this specificity, so this is how you can write down the answer and get your answer. So if you keep your palm towards, if you keep your thumb towards the east and be upwards, then your palm faces towards you, so which means it's the south. So this is how you can represent the direction of the magnetic field and solve the problem. Next, let's talk about magnetic field when you have two wires. So, or magnetic field when you have a current passing through a wire, current carrying conductor. For a current carrying wire in an external magnetic field that also undergoes a magnetic force, that is given by F magnetic equal to BIL. So B is the magnetic field, I is the current, and L is the length of the wire or length of the conductor. Now when you have two parallel wires, what happens is the magnetic field that is produced by one wire can apply a force on the other wire. So this is one way. So what happens when you have two wires? For example, let's say if I have two wires, the magnetic field that is produced by one wire can apply a force on the second wire. So the force that is applied on the second wire, what type of attraction will be there? So because there is a force being applied, which means that they act as magnets, and because you have two magnetic fields, we have to know whether they attract each other, whether they repel each other. Now if the currents are in the same direction, the two wires will attract one another. Now if the currents are in the opposite directions, the wires will repel each other. So one of the best uses of these is loudspeakers. Loudspeakers use magnetic force to produce sound by rapidly vibrating and rapidly changing the direction of current between the two wires by creating a force. So this is the example here. So when you have both currents carrying the same wire, both will be in the same direction, which means that the force applied will go towards each other, and when it's in the opposite directions, they will repel each other. So let's take an example problem. So you have a wire 36 meters long carrying a current of 22 amps from east to west. So focus on the direction. If the magnetic force on the wire due to the Earth's magnetic field is downward towards the Earth and has a magnitude of 4.0 times 10 to the power negative 2, find the magnitude and the direction of the magnetic field at that location. So you have the length of the wire, which is 36 meters, the current, which is 22 amps, and you have a magnitude B, which is 4.0 into 10 power negative 2 Newton. So they are asking us to find the magnetic force, so Fm. So they're asking us to find Fm. So let's try and solve the problem. So we know that Fm, the formula for it is Bi times L. So let's substitute all the values. B here is 4 times 10 to the power of negative 2. Oh, I'm sorry. They have given us actually the force, Fm. They are asking us to find B. So we have the formula Fm equals BIL. So B equals Fm by IL. So Fm here is 4 times 10 to the power negative 2 by I is 22 amps times 36 meters. So calculate the value. You have 4 divided by 22 divided by 36 times 0.01. So the value becomes 0. So 5.05 times 10 to the power negative 5 Tesla. So this is the magnitude of the magnetic field that is acting from downward. Now this is the wire. So the wire is conducting current from east to west. So which means that we have a current carrying wire in this direction here. So this is east and this is west. So it's going from east to west, which means that the current flowing is in this direction. So this is the current I. Now what is given here? The magnetic field is downward. So the magnetic field is downward in this direction here. B is downward. So the magnetic force acting is downward. So this is Fm. Fm is downward. Now how would the magnetic force be? So what you can do now is put your hand in such a way that the thumb indicates the current flow. So where you would put it downward, facing it downward. So basically put your thumb towards the from east towards west and put your palm facing downward. So the other four fingers will indicate the magnetic force. So that magnetic force indication here will go this way. So this will be the magnetic field B. So if this is east to west, then B here is pointed towards the north. So this is the direction. So this is downward and this is to the left. Sorry, this is towards the west. So which means that this will be towards the north. So we still use the same right hand rule. So that's how we can choose the system. So with this, we end our lecture on magnetism. So I'll see you again in the next lecture.